I'm going to introduce you to a set of functions that more than likely is a set of functions that you haven't dealt with in the past at all, or if you have, probably not very much. So I'm going to start from the very beginning here. These set of videos don't have any calculus attached to them. Every bit of this is pre-calculus. So we're very comfortable being in the XY coordinate plane. We've been in the XY coordinate plane, many of us, since we were in 8th grade. So we're very comfortable with locating points in this plane. We understand that in rectangular coordinates, we know that we break the plane into a grid of horizontal and vertical lines. We can locate a point by simply identifying the intersection of a vertical and horizontal line. We know that the vertical lines are our x coordinates and the horizontal lines are our y coordinates. So if we are looking for any one particular point in the plane, it has one and only one address. It has one specific unique x coordinate and one specific unique y coordinate. We know that the independent variable in this notation is listed first, and the dependent variable is listed second. So we're really comfortable with this coordinate system. In polar coordinates, which is where we are going to graph our polar functions, the plane looks a little different. Here we break the plane up with circles that are centered at the origin. Here's the origin. And rays that emanate out from this origin at angle measures. These are all angle measures in radians, starting with an angle measure of 0, which from trigonometry we know is also the angle measure of 2 pi. So in polar coordinates, when dealing with polar functions, your unit circle and your exact values become really important. So make sure that you do a review of this information if you need to, because your exact values, your radian angle measures, all of that information from trigonometry is going to play a big role when dealing with polar functions. We can locate a point in the polar plane as the intersection of one of these circles and a ray. So the coordinates here are the radius of the circle and the angle measure from the standard ray, which has an angle measure of 0 or 2 pi. So the coordinates look very much like coordinates that we're used to, but locating them in the polar plane is a little bit different. Here we know we have a radius of 1 for this point, and we have an angle measure of pi over 6. So we know that we're going 1 unit out from the pole. Here we're shown concentric circles, and this must be 1/4, 1/2, 3/4, and 1 unit from the pole. And we know that we are from the standard initial ray, we have a theta measure of pi over 6. And that locates the point in the polar coordinate system for us. So the polar coordinate system is based on distance from the point of origin. We've always called that 0, 0. In the polar coordinate system, it's actually called the pole. Our polar coordinates are radius, comma, angle measure. And a difference here that I want to note, and we'll talk more about this later, but it is true that we are going to be talking about functions of theta. Polar functions are functions of angle measures, functions of theta. So where we're used to having independent, comma, dependent coordinates of our points, this is reversed. R is the dependent variable, It is the output value, and theta is the independent variable in polar coordinates. Why they are listed opposite from xy coordinates, I really don't know. But r is the dependent variable where theta is the independent variable. If we have some point P in the polar plane, we're going to locate the coordinates of P by finding r, the distance from the pole, and by finding theta, the angle measure from the polar axis. So not new information to us, especially if we have dealt with trigonometry, because we can drop an altitude and we're in a right triangle. This would be our x value, this would be our y value. And so what we find when we're dealing with polar functions is usually we don't have a complete separate coordinate system. What we find is that we graph these functions in the xy plane. We don't draw our concentric circles. We just superimpose in our minds the polar coordinate system on top of our very, very, very detailed knowledge of the Cartesian coordinate system. So the first coordinate here, if we have the point 2 comma pi over 6, the first coordinate, r equals 2, is the distance of that point from the point of origin. If we're in the Cartesian plane, that is x equals 0, y equals 0. Superimposing the polar coordinate system, that is the pole, which is where r equals 0. The second coordinate, theta equals pi over 6, indicates the distance or the angle measure from the positive x-axis. And we are going to rely heavily on our trig knowledge, so make sure and review if you need to. Remember from trigonometry, positive angle measures rotate counterclockwise from the x-axis, where negative angles rotate clockwise. We're going to need our exact value angle measures. We're going to need to have a good idea of where pi over 6, pi over 4, and pi over 3 are in the plane. So review your unit circle. Again, we superimpose just in our minds the polar coordinate system in the xy coordinate plane. But we are going to draw these polar functions in the Cartesian plane using our knowledge of angle measures from trigonometry and the tick marks along the x and y axes to help us determine, even though we're not going to draw the circles, we won't be drawing the circles, but we can use those tick marks to help us determine our r values, the distance from the pole. So with a little bit of practice, you'll be doing this no problem. The difference between the Cartesian coordinate plane, where every point in the plane has one unique address or coordinate, in the polar plane, we're going to have infinitely many, because we can rotate around this circle infinitely many times. And when we get back to the point, we have a whole new angle measure. And we can rotate in the negative direction around this circle, giving us a completely new look. Now, it's not an actual different point in the plane. It's just a new coordinate that maps us to the exact same point in the plane. We can also talk about starting at the pole and going, instead of a distance of 2 in this direction, we could go a distance of 2 in this direction. We could call this positive direction and that negative direction as far as the radius is concerned. And then we could rotate from there around until we find the angle measure that's going to map us to that point. So there are infinitely many representations for every single point in the polar plane. This is really not an issue or a problem for us. most of the time we are only going to be concerned with what is happening within one rotation. Now, rarely are they going to get you outside of that one rotation, and if they do, it's not going to be a big deal. We've done that before when working with trigonometry, so this is not going to be a big issue, but it is something that I wanted to make sure that you consider and think about, because we are so used to every point in the plane only having one label or one address. Here we could have infinitely many. Most often they're going to be very straightforward with those coordinates. So, how are polar coordinates and Cartesian coordinates related? Well, I've already kind of let that cat out of the bag. They are related from our knowledge of trigonometry. This is not new to you. If there is some point P in the plane, and we drop an altitude, that vertical distance we're going to call y. That horizontal distance we're going to call x. We're going to draw a ray from the point of origin to the point in the plane under discussion. We're going to call that distance the radius, or r. And then we're going to have an angle measure from the positive x-axis counterclockwise till we hit the ray that goes through from the origin through our point. And that angle measure is going to be the angle measure from the x-axis. And we know from trigonometry that the cosine of our angle measure is adjacent over hypotenuse, and the sine of our angle measure is opposite over hypotenuse. We know that we can put x in terms of r and theta. For the unit circle, remember we talked about this, the unit circle is so powerful because that's where r equals 1. For y, we put y in terms of r and theta. Again, for the unit circle, r was 1. We don't always need to count on that, however. So there's the relationship. If I was given an r value and a theta value, I could find the equivalent x coordinate and y coordinate that was that r comma theta value. So in other words, going from polar coordinates to Cartesian coordinates is pretty straightforward. We're already comfortable using that. Going from Cartesian coordinates to polar coordinates just requires a little more trigonometry that we already know. So let's practice that, knowing that the tangent of theta is always opposite over adjacent, and knowing that any circle in the plane centered at the origin is x squared plus y squared equals r squared. If I have an x coordinate and a y coordinate, then I can use these two equations to find an equivalent polar point coordinate from the Cartesian ones. So let's work a couple of these examples. Find the Cartesian coordinates corresponding to r equals 4 and theta equals pi over 6. Well, remember, this is the most straightforward because we know our x coordinate must be r times the cosine of the angle measure, and our y coordinate must be r times the sine of the angle measure. So this is going to be really straightforward. X has to be 4 times the cosine of pi over 6, and y has to be 4 times the sine of pi over 6. So it is going to become really important that you go back and review your exact values if you don't remember. The cosine of pi over 6 was root 3 over 2. The sine of pi over 6 was 1/2. So 2 root 3 is the x coordinate, 2 is the y coordinate. So the corresponding Cartesian coordinates are 2 root 3, comma 2.